Okay, so in this section we want to show why sulfur and why phosphorus can make more bonds than you would predict based on the octet rule. So the first thing we want to look at is the electron configurations for both of these molecules. So we can see that phosphorus has 15 electrons that we've got to account for. Sulfur has 16 electrons. So if we do the electron configuration for phosphorus, we can also see that these are both p block elements. And so this is going to be what, third row? So this is going to end in 3p, 3 for phosphorus, and 3p4 for sulfur. And so if we walk these two back, these are going to have 3s2 that's going to be filled, 2p6, 2s2, and 1s2. We can add these up, 10, 12, 15, so we've got 15 electrons there. We'll have the same thing here, and we've got 10, 12, 16 electrons for our sulfur. So there's our electron configurations. The one thing though that's not shown in these electron configurations of sulfur and phosphorus is that the third subshell does have the d subshells. They're just not being used because there's no more electrons to finish filling it. But it does exist. So essentially, there's no electrons that are in the 3d subshell. So it would be a 3d0 submarking. But they still exist. So if we're looking at sulfur as our first example, we can see the valence electrons for sulfur are in the s and the p orbitals of the third subshell. That's the highest subshell. Same thing for phosphorus, right? The 3s2 and the 3p3 are the valence electrons. So phosphorus has 5 valence electrons, right? It's got the 2s2 or the 3s2 and the 3p3. Sulfur has 6 valence electrons. And if we fill these in as a Lewis structure, we would put them around the sulfur, 1, 2, 3, 4, and then we would keep going and these would start to pair up 5, 6. So typically to get to the octet state, sulfur would like to create 2 more bonds with another atom to share here, and then it would be full. In a similar way, phosphorus also wants to do the same thing. It's got 5 valence electrons, so we start filling these guys around the phosphorus. It's got to start pairing here. So now we have 3 places with phosphorus. So to reach the octet, so based on the octet rule, this one would want 2 bonds. This one would want 3 bonds because there's 3 places for it to be sharing. So this is based on our octet rule. And these rules do apply, and these 2 elements can make 2 bonds or 3 bonds for phosphorus. However, if we look at the d orbitals, they're just sitting there empty. And so if we're drawing out our electron configuration a little bit more, we know our 3s subshell has 2 electrons in it with opposite spin. And then this p subshell has 4 electrons in it. So the p subshell has how many orbitals? Hopefully you said 3. Right? And they're going to be separate until they have to start pairing. So we've got 1, 2, 3 electrons. The 4th electron has to pair right there. Now we do have the d orbitals that are present. How many d orbitals are there? Hopefully you said 5. 1, 2, 3, 4, 5. Normally they sit empty. So that would be the outer shell for sulfur. For phosphorus, looks very similar. We've got 3s, and both of these guys are in there. So we've got the 3s electrons. And then there's only 3 electrons in the p orbitals. But there's still 3 of them. And they each go in separately. And then the d orbitals, again, are going to be sitting empty for phosphorus as well. So they're just hanging down there. So what happens when these guys start having expanded orbitals and being able to take more than one electron is that these guys are going to split up. We've got two pairs of electrons that are in the valence shell that are paired. The one in the s orbital and the pair that's in the p orbital right here. If we split them up, we get more opportunity to share electrons. So if one of these electrons kicks down into the d orbital and it moves down there, so we're going to put this one down here, that would open up two extra spaces for bonding to occur. This guy would no longer be paired, right? It's open, so we could pair another electron here, and now this guy would also be unpaired. So we can do two bonds, or if we split up the p electrons here, we could form two more bonds. So sulfur, if we do this, could also form 4 bonds by electron splitting. We could also split this pair up here and use one of the d orbitals as well. So we could use this other empty d orbital. It's like him saying, I'm tired of being paired with you, I'm going to go to a different apartment. And so this one comes down and it's wanting to live alone. Now this one is available for bonding, and this electron is also available for bonding. So now you can have 2 bonds, 4 bonds, or if the electron configuration shifts to this state, you could have 6 bonds that are shared between other elements. So sulfur is special. The octet rule would give us 2 bonds, but we can break the octet rule by doing electron splitting, and we can have 4 bonds or 6 bonds occur. You can see that with our phosphorus, we're a little bit more limited. We only have one that's actually sharing right here, and that's in the s orbital for the p subshell. And so we can shift down 1 electron then into these free d orbitals down here. And so that guy is going to move down here, which opens up 2 extra spaces for sharing of electrons with other atoms. So phosphorus normally forms 3 bonds with the octet rule, or if we're breaking the octet rule with electron expanding, we can have 5 bonds, right? Because this one can share now, so we've got 1 bond that can form here, 1 here, 1 here, 1 here, and 1 here. So that's a total of 5. So phosphorus can form 3 bonds, or it can form 5 bonds, depending upon how the electrons are going to shift. So this is the reasoning why you can have these expanded orbitals, and sulfur and phosphorus can have extra bonding opportunities.